Okay, so picking up on day two, we are going to talk about some of the properties with derivatives and integrals with these power, power functions. Okay, so we have this power function because we have like our regular old infinite series, and now we have the x's involved. And let's say, like, again, we have this radius of convergence kind of going on, where we're centered from, we add and subtract. And these endpoints, we said those are the wild card. They can do lots of things. But what's super, super cool is that if I take the derivative of what I had, I'm still going to have the same radius of convergence. It's just the endpoints could be different. Same thing if I took the antiderivative, it's still the same radius of convergence. It's just the endpoints could behave different because those are the ones that are crazy. So how do I take the derivative? Well, this a sub n part, we're deriving with respect to x. So the a sub n part's like a coefficient, and it just gets to woohoo, go along for the ride, because that's what coefficients do. So the a sub n part goes along for the ride, and then I take and I bring the n down and subtract 1. And then if you want to try to simplify it, what's really cool is a lot of times that if I plug in 0, do you see how that term is just 0? So this could be the same exact thing as starting at 1. Now, that's not always the case. You can't always just say that those are equivalent, but here they are. So on a multiple choice test, a lot of times they're going to go and they're just going to, hey, 0 is just a 0 term. So boom, let's go to the next one and just start there because it's the exact same thing. Okay. So if I look at this one, when I take the derivative of f of x, I leave everything the same to start with. The a sub n goes along for the ride. I bring my n down, and then I subtract 1. And then I see that if I plug in 0 here, I get out 0. So that's the exact same thing as just going ahead and waiting and starting, or skipping the 0 and starting at the 1, because now the 1 will start giving me terms. So these will have the same like radius of convergence. All I know is that the endpoints can behave differently. Oh, how did I just do that? Oh my gosh, I didn't mean to do that. Make them smaller again. You don't want that big. This is what oh, now I'm gone. Okay. How did I do that? You guys. Okay, well, I'm gone. Okay, so here. When I take the integral, I'm basically going to now, again, the a sub n goes along for the ride. And so this one right here, I add 1 and divide just like we would have. And then I have this plus c. So if I was looking at this f of x one up there, and I wanted to take the antiderivative, a sub n goes along for the ride, I would add 1 and then divide by what I had. Okay, now this 0 does give me a term, so usually, almost always it does, so usually we have to keep it there. We don't get to jump forward. Okay, so the interval is the same, the endpoints just could be different. So here's an example. It says, here we go, here's our power series, and it wants you to find f prime of x. So I'm going to just kind of look at this so that we see clearly that our a sub n is this 1 over infinity, and then I have it times x to the 2n. So there's my a sub n part that's going along for the ride. And now I can take and bring this 2n down, and then that's x to the 2n now minus 1. So I want to find that, and I can see that it is right there, and it is D. Let's say that none of these matched exactly, then they may have tried to start at a different n value. So you may have to like jump forward to 2 and rearrange and then see if it matches. But typically they will match what you get here, but if not, that could be the case. Okay. Um, we're gonna skip that one for now. We can do it in class if we want to, but let's go ahead and do this next one. What's tough about this one is that it's harder to see, like, I have this 1/4 involved, so you can either like separate it out to see that you have like 1/4 to the n and then x to the n. So that way you can see the a sub n and then the power series part. And a lot of times people want to do that. Otherwise, you're going to have to work with the chain rule sum, which isn't that bad either. So it's kind of up to you on what you prefer, to just rewrite it to see the a sub n or to do the chain rule. So I'm going to go ahead and rewrite it, and then I'll show you the other way as well. So if I'm looking to take the derivative, I leave everything the same to start, and then this is now going along for the ride. And now I'm going to take it times n, x to the n minus 1. And when I do plug in 0, that is a 0 term, so I can go ahead and jump to 1 if I want and get to this. Oops, sorry, I left off my n. I left it off both times. Okay, there. So that n and that n stays. Everything stays the same. I can just jump forward because that's a 0 term. Okay. So that could be one way, or I could say if I left it just as it was, I could take the derivative. So I'm going to bring my series down, my n down, subtract 1, okay, and then multiply by the derivative of the n side, which is 1/4. And this actually ends up becoming the exact same thing if I reduce that and put it all together. Okay? And I could start at 1 here as well because that first term is 0. Okay, so then the integral, I'm going to use this one now for the integral. So now that's x to the n plus 1 over n plus 1, and I do need those terms because they are there. Okay. So personally, I like to get it simplified. My a sub n is pulled out, and then take the derivative and antiderivatives, but that's completely up to you. Sometimes it's easier to just look at the term by term and just derive kind of term by term. And here I just want to show you what I mean by that. So here is an AP example. This was my series going on, and they gave me some of the terms, and they wanted me to find the first 3 non-zero terms for the derivative, and this guy was g. So when I took my g prime of x here, the derivative there is 1/3. The derivative there is 3/5 x squared. The derivative there is 5/7 x to the 4th. So that's kind of easier to see term by term what that derivative is, okay? And then I still, though, need to take the derivative of that for the general term. So for that, I can see that all of this is my a sub n, and then there's the power part. So I'm going to have all of that going along for the ride. And I'm going to take the derivative of that piece now. So bring this down and subtract 1. So there's the first 3 terms, and then there's the general term. So that's where I mean, like, sometimes it's easier just to see that these derivatives. And in fact, like if I plugged in 0, 1, 2, 3, I'd be getting out this. Okay. Let's do a little bit harder one. So this is from an AP problem as well. So here it gives me f of x. Oh, that's kind of hard to see. That's x to the 3rd. It got a little bit moved over. And then minus x to the 6th over 2 plus x to the 9th over 3, etc. So it wants me to write the first 4 non-zero terms for the series for f prime of t squared. So if I asked you to find like f prime of some value 4, what's the first thing you would do? Would you plug in the 4 and then take the derivative? No, you would take the derivative. So you have to take the derivative first, then go plug in the value second. So let's go ahead and take the derivative. And I'm going to go ahead and go term by term. And I'm simplifying as I go because I can see 9 over 3 is 3. This part goes along for the ride. And then 3n x to the 3n minus 1. And I could cancel out those n's if I wanted to. Okay. So then, after I get that, then I can plug in my t squared. So right now, I'm just working on this first sentence. Then I'll go to the next sentence. So now I can plug in my t squared. And I forget how many it wanted. First 4, so there's 1, 2, 3. And I didn't even have to get that general term. It just wanted the first 4 non-zero terms. So there we go. Then it tells me that g of x, so there's that first sentence. Then it says g of x is equal to this right here of what we just found. So I'm just going to write in what it tells me so I can see a little bit better what it's saying. dt. So it says g of x is equal to that. Use the first 2 non-zero terms to approximate g of 1. Okay, so let's go see here. G of x tells me I need to take the integral. So I'm going to integrate. And I can keep going. And I'm going to evaluate that from 0 to x. So the x part would be the 3/5 x to the 5th minus 3/11 x to the 11th, dot, 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 minus, oh, what happens when I plug in 0? That's all just 0, so it goes away. So here I get that g of x is this. And it keeps going. So then let's see what it says. It says use the first 2 terms of that to approximate g of 1. So g of 1 is approximately 3/5 times the 1 to the 5th minus 3/11 times the 1 to the 11th. And that's the end for that. That was a lot though, okay? So that's part C. So now let's go look at part D. If the Maclaurin series for G, so that's what we just did, is evaluated at x equals 1, is a convergent alternating series with individual terms that decrease in absolute value to 0. Well, they've kind of already told me that if it's convergent, okay, with alternating. But sure. Show that your approximation in part C must differ from G of 1 by less than 1/5. So this is talking about the alternating series error bound, which says that my exact minus my approximation that I just got, which was the 3/5 times 1 to the 5th, minus the 3/11 times 1 to the 11th, has to be less than or equal to the next term, which was 3/17, evaluated at that 1 still, times 1 to the 17th. And it says, if I looked at that, that was just 3/17, and it wants us to show, now we need to write this, so when you're in your quizzes or your tests, you need to tell me, yes, that is less than what they said of 1/5. So show that it is less than 1/5. 1/5. And yes, 3/17 is smaller than 1/5. That's all. The alternating series just says, go to the next term, plug in the 1. So my next term was right there, and I plugged in the 1. Let's go to the next one. Here is this Taylor series, centered at 1, which I could see. And it says it converges to f of x for this right here. And r is the radius of convergence. Okay. Find the first 3 non-zero terms and the general term of the Taylor series for f prime. Right. So this didn't give me any term by terms. I'm going to just rewrite what it is that they did give me, where I can clearly see my a sub n part. So that's all my a sub n, and then here's what makes it the power. Okay, so it wants me to take, and it says that this is approximating here for the f on this radius of convergence. Okay, so I want to find the first derivative, and it didn't give me term by term, so this is probably easier to just do in general. So this part goes along for the ride. And now I derive this. And I can simplify that. Sorry about that. I can simplify that because the ends now cancel out. So this right here. Okay. So now it wants the first 3 non-zero terms and the general term. So I'm going to go ahead and plug in my 1 to everything. All the ends. And then I'm going to go to 2. And then I'm going to go to 3. Oops, sorry, I forgot to subtract 1 there. Sorry. And keep going and get the first 3 non-zero terms. And I want to see if you can do it, so pause me and then I'm going to write what I got. And that's what I wrote. All right, so read the next one, and then let's try it together. Okay, so they gave me this function, and as soon as I see this, man, I am really thinking that this is like my a over 1 minus my r. Okay, it's just popping in my mind. It's kind of set up right there with that whole geometric. Okay, and then they're giving me that it converges, and I'm even seeing that the endpoints both diverge. So look at this. Is this geometric? Yes. This is basically kind of like this part right here. So my a is my 1 and my r is -1. Okay, so I can see that this is a geometric going on. Let me show you a little bit better way. You're gonna love this. So if this is my a, then I have 1 minus my r, 0 to infinity. See if you get that. Watch when you plug in 0. And plug in 2. Or 1. then plug in 2. Oh, do you see how it matches? Okay. So this is like, I'm kind of like putting all this together and really looking and seeing that I have a geometric power series going on. And that's going to be important that I can identify that in the problem, because it's going to make my life so much easier. All right, so A, find the first 3 non-zero terms in the general term for f prime of x. So on this one, I would go term by term. That goes to 0. There I go. Hopefully you could do that one pretty easy. Okay, part B says use your results to find the sum. So I'm using it to find the sum of the series for this guy right here. Okay. Well, what is this? That's the first thing I kind of want to look at. What did they do here? I'm seeing that I have this -3, 6, 9. There's -3, 6, 9. So it looks like they're using this derivative. And then what are they plugging in for x? Do you see how they're plugging in a 1/2? So now this is like 1/2 squared, 1/2 to the 5th, 1/2 to the 8th. You guys, I think this is one of the toughest ones here is this part B, okay? So here they are actually wanting you to find f prime of 1/2. So this is f. Let's go find f prime. And you can do the quotient rule, or you could rewrite it and do a chain rule. So f of x, I'm going to rewrite it and do a chain rule, is 1 plus x to the 3rd to the -1. So my derivative here would be -1, 1 plus x to the 3rd to the -2 times the derivative of the inside, which is 3x squared. So f prime of 1/2 is going to equal -1 is 1 plus 1/2 to the 3rd, all to the -2, times 3 times 1/2 squared. And you don't have to simplify that. You can leave it. If you did simplify it, I got -16 over 27, but you don't have to. Okay. C, what's the first 4 non-zero terms in the general term now for the antiderivative? So now go back up to here and do the antiderivative. So some of these aren't too bad, and like I said, B I thought was tough, but A and C, those should have been not bad at all. Okay. So now let's go to D. Use the first 3 non-zero terms found in part C to approximate that. So we are going to go x minus x to the 4th over 4 plus x. There's the first 3 non-zero terms, and it says to evaluate from 0 to 1/2. So this would be 1/2 minus half to the 4th over 4 plus 1/2 to the 7th over 7th. Okay, and then that's the first part, and then plug in 0, and that is 0. So there is this guy kind of approximating. And they're saying, show that this guy right here, what are the properties of the terms of the series that guarantee this approximation is within 1 over 10,000. So here we need to know that this series converges, right? So let's go see. We would want that the exact is from 0 to 1/2. There's my exact minus my approximate here. and is less than kind of the next term. So is this an alternating series test, or is this the Lagrange error bound? So I can see that these terms alternate, and in fact, this is going to converge by the alternating series test because the terms decrease in absolute value to 0. So I could actually just go to that next term and say, I know that that is going to be less than the next term, and this is the alternating series error bound. And guess what? You have to do one more thing or you're going to miss it on your quiz. You have to say that that is less than what they wanted you to find. And it is. This is actually 1 over 1, 2, 4, and that is smaller. Don't forget to put that last part on your quiz. Okay, so that's the end of day 2.